Although cooking meat kills the microorganisms in it, they may survive gentle frying and roasting, especially if the meat was not properly defrosted before preparation. Inspector of the U.S. Department of Agriculture test for Salmonella in the sample of chicken at meat packing plants. The sample is found to have a bacteria count of 25 colony-forming units per millimeter. The sample is kept at a temperature of 80 degrees, and 6 hours later the count is 20,000 colony-forming units per millimeter. So they want to find the instantaneous growth rate for the bacteria count in the sample, find the exponential model. Okay, so
when you do 20,000 divided by 25 and then divide that by 6?
So what's the model that we're assuming here? Exponential growth?
Yeah.
So the exponential growth, are we going to use this formula here? Is that what they want us to use?
Yeah, I'm pretty sure.
So what they're saying is, let's put this equation in. 20,000 equals let's see. So C represents the original amount, so you put 25 in for C, and then E is just that number. It's that Euler's constant, and the rate is what we don't know, and the time is in minutes or hours. T is measured in hours, so you raise that to the sixth. Yep, so to solve this for R, we're trying to get R by itself. We have to first divide by 25, and then to get these out of the exponent, remember how you get rid of that?
Square root it?
No, you take the natural log of both sides.
Oh yeah.
So you have 6R equals the natural log of 20,000 divided by 25. And then you divide the entire thing by R. Or I'm sorry, by 6. So the natural log of 20,000 divided by 25, be careful with the parentheses. Type this in first, and then divide that whole thing by 6, and make sure you have parentheses around 20,000 and 25.
Wait, what did it? Let me see if I...
So their answer, the rate is 1.114, and so our formula, that's 1.114, that's the answer for number 1. So, or part A. Part B, the answer would be F of...
25e to the 1.11.
Yep, 25e to the 1.114t. Yep.
Yeah.
And then what does the model predict the count will be after 4 hours? So now you plug in 4. Plug 4 in for t. T equals 4, so punch that in. See what you get. So your answer is 2154. And then part D says, how long will it take for the bacteria to reach 10 million? So now we're going to put 10 million in on the left side of the equation. So write 10 million equals 25 times e to the 1.114 t. So now we're going to divide both sides by 25. Then we're going to take the natural log, and then we're going to divide by 1.114. So in your calculator, very carefully plug in that entire expression, see what you get. And your answer here would be 11.58, rounded to 2 decimal places, 11.58 hours. And then it says here, find the doubling time for Salmonella. So doubling time means how long does it take to double? So if we started with 25, what would double be? So part E says find the doubling time. In order to find the doubling time, well, if 25 was your initial amount, then 50 would be your final amount. How long does it take to get to 50? So plug in 50 for your f of t. And then, of course, when you divide it, you'll get 2. 2 equals e to the 1.114t. And so do your thing. Take the natural log of both sides and then divide by 1.114. And that will give you t. So ln of 2 divided by 1.114. See what you get? And you'll get 0.62 hours. And there you go.